With the ever-increasing number of battery electric vehicles or BEV on the road, and with the trend of bigger batteries to increase driving range, it is unavoidable that EV charging stations have also started to become an important part of infrastructure. More EV charging stations can be found everywhere, especially at shopping centers and other public locations. Hi, my name is George Hariman and I am a systems architect with ROHM Semiconductor. Today, I will be presenting an overview of EV charging stations, in particular DC fast charging stations, and how ROHM's driver's high-power device portfolio helps in the design of efficient high-power solutions. There are two types of wired electric vehicle charging. The first is called AC charging. This type of charging takes power directly from the power grid and connects to an onboard charger or OBC mounted in the electric vehicle itself. The onboard charger converts the AC voltage into DC voltage, which is then used by the battery management system or BMS to charge and control the battery. The electronics for charging are in the OBC itself, and all components must meet automotive grade standards, AEC Q100. Level 1 AC charging, or L1, is normally found at home, where an EV is plugged into a standard outlet. For example, in North America, 120 volts AC. Estimated range per hour of charging is between 2 to 5 miles, which means it takes a very long time to fully charge a battery electric vehicle. Level 2 AC charging, or L2, can be found in many public places and also available at home, with special charger box installation. It uses either 208 volt, 3-phase, mainly industrial locations, or 240 volts AC, split phase, both industrial and at home in North America. Estimated range per hour of charging is between 10 to 20 miles, which is faster than the level 1 charging. The second type of charging is called DC charging, which currently is only available at certain EV charging stations. It is not available for residential charging. It first converts AC power from the grid to DC voltage via an off-board charger in a DC charger station. The DC voltage is then directly provided to the battery management system or BMS within the EV. This allows optimization of the off-board charger at the DC charging station to scale up and deliver much higher power to the BMS. The electronics for charging are located at the charging station itself. Components designed into this charger shall meet industrial grade standards. This presentation focuses mainly on ROHM's power device for DC charging stations. DC fast charge, sometimes called DC level 1, which covers power levels from 20 kilowatts to 150 kilowatts. DC fast high power charge, or DC level 2, that provides levels up to and beyond 350 kilowatts. These DC fast charger combined are also known as level 3 chargers. These DC fast chargers can charge an EV in a much shorter time and can charge up to 240 miles of range per hour of charging. Various different charging systems regarding connectors and protocols exist globally depending on the region. For DC fast charging, they are Combined Charging System, or CCS Type 1 in North America and CCS Type 2 for the European region and other regions, with an output voltage up to 1000 volts and up to 350 kilowatts of power delivery. The CHA-DEMO in Japan, with output voltage ranging from 400 volts to 1000 volts with up to 400 kilowatts of power delivery. The GB/T20234.3 in China, with output voltage ranging from 750 volts up to 1000 volts with up to 250 kilowatts of power delivery. And the Tesla's supercharger network, version V3, with output voltage of 480 volts up to 250 kilowatts of power delivery. The Tesla connector system, commonly known as the North American Charging Standard or NACS, is in the process of becoming a standard SAE J3400. The voltage is expected to be 500 to 1000 volts and to be standardized by the end of 2023. The ever-increasing demand for EVs to drive longer distances with a single charge has steadily increased EV battery capacity over time. At the same time, the trend towards higher power DC fast charge station has also increased. In order to meet the higher power demand, DC fast charging stations must contain multiple power supply units or PSU as shown in the diagram above. Each PSU must provide more than 40 kilowatts of power in order to supply a total of more than 350 kilowatts. The circuit topology trend is to use a three-phase Vienna rectifier along with silicon carbide devices to provide a high-efficiency solution with better thermal management capability. This block diagram shows a typical setup for a unidirectional DC fast charging industrial station. The upper portion shows the main power path. Power is taken from the three-phase AC supply line and converted from AC to DC via a PFC or power factor correction stage, before then being further converted through a high voltage DC to DC converter stage. In the image above, the PFC stage is shown as a Vienna rectifier configuration, and the DC to DC stage is shown as an LLC isolated converter. The lower portion of the diagram shows auxiliary and other circuitry, which includes control circuits for the power stage as well as the lower power AC to DC converter and other interface-related circuitry for the display and communication buses. This block diagram on this page shows a typical setup for a bidirectional DC fast charging industrial station. It allows power flow not only for charging an EV, but also to charge back from the EV to the electric grid. In the image above, the PFC stage is shown as a three-phase bidirectional configuration, and the DC to DC stage is shown as a dual active bridge or DAB resonance isolated bidirectional converter. First stage of the power conversion in a DC fast charging block diagram is the high voltage AC to DC conversion stage. A power factor correction or PFC block accomplishes this AC to DC conversion while also increasing the power factor or power quality. The Vienna unidirectional AC to DC converter utilizes both diodes and FETs, while the three-phase bidirectional AC to DC PFC uses only FETs. Various ROHM part numbers for silicon carbide MOSFETs, silicon carbide Schottky barrier diodes, or SBD, superjunction MOSFETs, insulated gate bipolar transistors, or IGBT, and gate drivers are shown in the table above, corresponding to each type of high voltage AC to DC stage. The second stage for power conversion in a DC fast charging block diagram is the high voltage DC to DC converter. Both the LLC converter and dual active bridge or DAB converter uses FETs on the primary side. The LLC converter, which is unidirectional, uses diodes on the secondary side, while the dual active bridge or DAB, which is bidirectional, uses FETs on the secondary side. Various ROHM part numbers for silicon carbide MOSFETs, silicon carbide Schottky barrier diodes or SBD, superjunction MOSFETs, and gate drivers are shown in the table above. Silicon carbide, or SiC, is emerging as an ideal semiconductor for power devices used in EV charging stations. As a wide bandgap semiconductor, silicon carbide provides 10 times the dielectric breakdown compared to silicon devices, allowing higher voltages in a smaller footprint. In addition, higher temperature stability allows silicon carbide devices to reliably operate at up to 200 degrees Celsius versus just 150 degrees Celsius with traditional silicon devices. And silicon carbide enables operation at much higher switching frequencies due to the significantly lower switching losses. making it possible to reduce the physical sizes of electromagnetic components such as inductors. The main difference between silicon and silicon carbide devices is that silicon carbide has a higher dielectric breakdown electric field at 2.8 megavolts per centimeter compared to only 0.3 megavolts per centimeter of regular silicon. Because of this, power devices built with silicon carbide can be made shorter, to just 1/10 the length, which then further reduces on resistance and ultimately conduction losses. In addition, silicon carbide devices have much lower reverse recovery charge, resulting in lower switching losses. In fact, up to 70% lower switching losses can be seen with silicon carbide FETs compared to solutions using insulated gate bipolar transistors or IGBT plus fast recovery diodes or FRD solutions. Silicon carbide devices provide high voltage switching voltage conversion with lower losses versus their silicon counterparts. With the advantage that silicon carbide brings on the device level, it is easy to see how these benefits extend directly to multiple system levels. Lower resistance devices allow for smaller size and higher switching frequency. Reduced switching losses enable operation at much higher switching frequencies, making it possible to reduce the size of passive components used in the circuits. Last but not least, with lower losses, it is possible to operate at higher temperatures while at the same time reducing the thermal solutions required. ROHM supplies two types of silicon carbide devices: Schottky barrier diodes or SBDs and field effect transistors or FETs. These are available in wafer or bare die format, discrete package part format, and full power modules. A wide voltage range is offered from 650 volts up to 1700 volts. On resistances as low as 8 milliohms are provided in our latest 4th generation silicon carbide FETs, while our silicon carbide modules go down all the way to 3 milliohms. ROHM's considerable portfolio of silicon carbide devices allow power electronic designers to select the ideal solution based on set requirements. Here we can see ROHM's lineup of new 4th generation silicon carbide FETs. A wide voltage range from 750 volts up to 1200 volts is offered with on resistances as low as 13 milliohms typical. Packages include two through-hole types, the TO247N and the TO247-4L, along with the surface mount package, the TO263-7L. This allows users to select the ideal product to meet their set needs. Parts are in stock and available to purchase on various distribution websites. ROHM's silicon carbide MOSFET comes in two varieties of leaded TO247 package. The latest TO247-4L package has 4 leads. The extra lead is dedicated for connecting the gate driver directly to the source of the internal silicon carbide MOSFET. This allows the driver to bypass the parasitic inductance normally encountered at the power source pin. The result is the reduction of switching losses, and thus the ability to drive 4-lead silicon carbide MOSFETs at even higher switching speeds compared to conventional 3-terminal types. Simulation models such as SPICE, thermal, and Plex models are available. These models will allow system designers to verify their design with the selected product part numbers. In addition, PCB CAD library symbols and 3D models for the 4th generation silicon carbide MOSFET lineups are available. This will allow rapid design-in of selected parts into the final PCB design. Offering these models allows system designers to easily facilitate the design process. These design models can be accessed on our website, rohm.com. This table shows ROHM's family of silicon carbide power modules. These modules contain multiple silicon carbide dies connected in various configurations. Different models feature a variety of internal topologies such as half-bridge and chopper or boost circuits. Voltages from 1200 volts to 1700 volts and current ranging from 80 amps to 600 amps are available to support high-power applications. Simulation models for the entire lineup are also available, including Plex, SPICE, thermal models, and SPICE simulation evaluation circuits, of all which can be found on our website, ROHM.com. 3 new silicon carbide power modules in various configurations are soon to be introduced by ROHM. These 3 module products are designed for automotive traction inverters, onboard chargers or OBC, DC-to-DC converters, and other systems to provide value beyond conventional solutions. More detailed information about these upcoming silicon carbide power modules will be explained in an online presentation on October the 2nd through the 6th at the All About Circuits AAC Industry Tech Events. Please visit the webpage shown in the link above to register and learn more about our new product modules at the time. Shown here is ROHM's lineup of silicon carbide Schottky barrier diodes, or SiC SBDs. Voltage ranges from 650 volts to 1200 volts, with rated currents from 2 amps to 40 amps. The total capacitive charge, or QC, of Schottky barrier diode SBDs is small, reducing switching losses while enabling high-speed switching operation. In addition, unlike silicon-based fast recovery diodes, where the reverse recovery time, or TRR, increases along with temperature, the silicon carbide SiC SBD devices maintain constant characteristics, resulting in better performance. Both through-hole and surface mount types are available as shown. The broad portfolio supports a variety of design specifications. Evaluation boards for ROHM's 4th generation silicon carbide MOSFETs are available in half-bridge topology. Both TO247N and TO247-4L through-hole packages can be evaluated depending on the EVK part number shown. These evaluation boards include an adjustable gate driver with isolated power supply to perform double pulse testing. Onboard gate driver and peripheral circuits reduce the number of man-hours required for design and evaluation. They are available for purchase on various distribution websites. This page shows an evaluation board for the surface mount TO263-7L package silicon carbide MOSFET parts. The evaluation board is configured in a half-bridge setup and thus allows evaluations in different operations, such as buck, boost, synchronous buck boost, and inverter operations. The board is equipped with 2 silicon carbide MOSFETs, the SCT4036KW7, isolated gate driver, the BM61S41RFV-C, isolated power supply required for the gate driver, LDO for 5-volt supply, and easy-to-interface connectors for PWM signals. Similarly, these evaluation boards include an adjustable gate driver with isolated power supply to perform double pulse testing. Contact ROHM directly to inquire about this particular evaluation board. Among power semiconductor devices, in addition to MOSFETs, there are also bipolar types, primarily used as semiconductor switches. The insulated gate bipolar transistor, or IGBT, is a bipolar junction transistor that is used for high-power switching applications. With respect to switching speed, bipolar types are suitable for medium speeds, while MOSFETs support the higher frequency range. The RGWXX-TS65X series of IGBTs from ROHM supports 650-volt operation and features the lowest VCE SAT that results in the lowest switching losses. Shown on this page is the RGWXX-TS65X series lineup of 640-volt IGBTs. Models both with a built-in fast recovery diode, which is denoted by a circle in the column titled FRD in the table above, and those without built-in diodes are offered. Those without built-in diodes require an external diode in the circuit in normal operation. Two leaded packages types are available. Rated currents up to 132 amps at the VCE saturation of 1.5 volts are offered. Another family of high-speed IGBTs offered by ROHM is the RGW-XX-TS65C series that integrates a silicon carbide Schottky barrier diode, SBD. This makes it possible to achieve much faster reverse recovery time compared to conventional IGBTs with a built-in fast recovery diode, or FRD. An example is the RGW0TSC65CHR that supports up to 96 amps with reverse recovery time of only 33 nanoseconds. This translates to even lower switching losses over standard fast recovery diode equipped IGBTs. The RGS series of IGBTs rated at 1200 volts are offered with an optional built-in silicon fast recovery diode, or FRD. The high voltage withstand capability of the RGS series allows it to connect directly to the high voltage supply on both the primary and secondary sides. The RGS series was developed with emphasis on low conduction losses. A primary application is the three-phase bidirectional PFC. The R60XX-VNXX series is ROHM's latest 4th generation 600 volts fast recovery Presto MOS. ROHM's Presto MOS are high voltage super junction MOSFETs that combine lower on resistance with optimized body diode characteristics for faster reverse recovery time. The R60XX-VNXX series features superior performance, achieving 35% lower area times on resistance and a 13% reduction in on resistance times gate charge compared to competitors and older generation models. Lower on resistance leads to lower conduction losses, while faster reverse recovery time results in lower switching losses. Both of these work together to increase overall system efficiency. The lineup shown on this page is the R60XX-VNXX, which includes products rated up to 77 amps, available in 5 different packages, including both through-hole packages and surface mount types. The highest current rated model comes in a TO247 package, features an on resistance of 42 milliohms and a reverse recovery time of 145 nanoseconds. An isolated gate driver is a special category of gate drivers normally used for high power or kilowatt applications. Primary functions include, first, boosting the strength of the microcontroller or DSP's output signal by increasing the voltage swing from 3.3 volts up to positive 18 volts and sometimes to negative 5 volts during turnoff, and also raising the current level from 3 milliamps to 3 amps or more. Secondly, providing the high current necessary to quickly turn on or charge and quickly turn off or discharge an IGBT or MOSFET power device. Lastly, deliver good isolation, separating the low-level microcontroller output signals from the DC bus voltage, often called the DC link. ROHM offers a few simple isolated gate drivers. These come in smaller package sizes and include basic functions such as active Miller clamping and under voltage lockout, or UVLO. Both single-channel and dual-channel versions are available. Isolated voltage as high as 3.75 kilovolts RMS are offered, with output drive current ratings up to 4 amps. ROHM also offers complex isolated gate drivers. These type of drivers incorporate additional features such as advanced soft turn-off, DSAT short circuit protection, and temperature monitoring. Some models also integrate flyback controllers with even more functions, including 2-level turn-off, temperature compensation, and selectable gate resistance. To help accelerate system design, ROHM offers not only evaluation boards of our gate drivers, but also PSpice and SPICE unencrypted models. Small size boards allow for easy connection and evaluation with customer boards. Please visit our website rohm.com to learn more about these resources. A number of ROHM isolated gate driver evaluation boards are available for purchase at various distribution websites, both for single and dual channel gate drivers. The table shown above shows different part numbers depending on what applications they are optimized for. ROHM evaluation boards greatly facilitate evaluation and the design and process of ROHM's product. Thank you for your time. Please visit our website to learn more about ROHM's extensive portfolio of products.